The Intel Curie microcontroller that powers the Arduino 101 contains integrated 6-axis gyro and accelerometer sensors. These sensors, combined with an also integrated digital signal processor and the provided library from Intel, make the 101 very good at sensing motion. The Arduino 101 motion sensing feature allows you to create gadgets that can do things like measure your daily steps, determine the orientation of the device, and detect shocks. In this lecture, I will demonstrate some of these applications to help you get an understanding of motion sensing with the Arduino 101. One aspect of using motion sensors is that the raw data that they generate are not readily useful because of the amount of noise that they contain. For this reason, smoothing and sensor fusion algorithms have been developed. These are algorithms that combine input from multiple sensors, remove the noise, and generate useful output. In the demo in this lecture, I will show you how to use one such algorithm to combine raw readings from the gyro and the accelerometer and output data that we can use to visualize the position of the Arduino 101 in space. Let's have a look at the details. In this lecture, we'll play around with the imu library that gives you access to the built-in gyro and accelerometer. Let's start with a simple example and go to Curie IMU and pick the accelerometer sketch, example sketch. So in here, we've got first the inclusion of the Curie imu.h, gives us access to the library, and we start the IMU object, set the range to be up to 2G, and in order to get readings from the sensors, all we've got to do is to read the accelerometer, and that will place the values from the accelerometer to these 3 integer variables that we have declared up here in the loop. We convert these values to floating point numbers and then display those numbers out in the serial monitor. That's all there is to it. We can convert accelerations to G instead of the raw value. So from the raw value, we use this formula here to convert the readings into a G-based reading, 2G range. All right, so let's upload that. And have a look at the monitor when it's available. It's not available yet. Let's try again now. Okay. So initializing the device as a new reading every 5 seconds. Let's change that orientation to this orientation. All right. Change that. You can see how the values change depending on the orientation of the device. Another sketch that I like from this set of examples is this one here that gives you the orientation. So this sketch here will take the orientation that is reported from, or will take the accelerometer readings reported from the sensors, and it will tell you what its orientation is. So it's uploaded. Let's have a look. So it says, for example, here that the connector is up. If I turn this upside down, then it will tell you that the analog pins, or that the connector is down. If I turn that up like that, you can see that the analog pins are facing up. So analog pins are up. If I turn this to the other side, then the digital pins are up. The digital pins are this set of headers. If I point the device upwards like that, then the connector is up and so on. So this is a simple way to detect the orientation of your gadget. And all you do is you just get the readings from the accelerometer itself, so we don't need the gyroscope, just the accelerometer, and then make various comparisons of these readings and determine which way the Arduino board is facing. The last IMU example I'd like to show you is one that combines output from the sensors and a processing sketch that graphically shows you the position of the Arduino board in space. And the other nice thing about this example is that it gives you a way to smooth out the noisy signal that comes from the sensors in order to generate information that is very useful out of the box. In this example here, I've got two sketches. One runs in processing on the desktop and the other one in the Arduino 101. Just remind you that I've got a section on processing elsewhere in this course that you can review if you're not familiar with processing. And what this sketch does in processing is to take readings from the Arduino containing information about the pitch, roll and yaw, and convert that into a graphical representation of the position of the Arduino in space. The Arduino is responsible for getting the readings from the accelerometer and then applying the Madwig filter on it in order to smooth out those readings and make them very useful for an application like this one. So Madwig is a library that implements a Madwig filter, which is the result of a PhD dissertation. Very interesting piece of work. I've got the links in the lecture notes if you are interested to know about especially the mathematics implementation behind the scene and what's happening inside the library. In the Arduino Sketch, we do a calibration so that the device knows what horizontal position looks like in terms of the G-forces applied to it. So when the application starts, when the sketch begins, we just need to put the Arduino on a flat surface and leave it there for a few seconds for the calibration to take place. And once the calibration is complete, then we go into a loop. We take motion sensor readings, just like in the previous example, by using the read motion sensor function, and then we apply the filter to those readings, and what comes out of that filter are the clean, yaw, roll and pitch values. And these are the values then that we pass to the processing sketch inside a comma delimited set of values in a single row that is transmitted serially to the processing sketch. So let's run the example. I will upload the sketch first to the Arduino. Okay, let's upload it. Let's bring up the monitor when it's available. All right. So we did the calibration, and these are the offsets after the calibration. So the Arduino now is good to go. I will close the monitor to release the serial port and then run the processing sketch on the other side. Okay, so you can see that the Arduino is now horizontal on the screen, and just turn it a bit to the side, and that movement is detected. You can see that it's out of calibration already. The Arduino is back horizontally on a flat surface, but the sketch takes a little bit of extra time to recalibrate itself, and now it's back into horizontal position on the processing side as well. And let's do some more movements. Okay, it's probably out of calibration as well again now, so put it back on the flat surface to recalibrate automatically, and that's a little example of how you can use this type of filtering to the raw output of the motion sensor in the Curie chip. On the processing side, there's not much happening other than drawing. So you've got the drawings of 3 rectangulars. Essentially, you've got the one that makes up the board, one that makes up one of the 2 headers, and the other one that makes up the other 2 headers. And depending on the pitch and roll, you adjust the positions of the 3 boxes in order to closely match the position of the Arduino. So with this, I conclude the lectures on the Arduino 101. I hope that you have a better understanding now of what the Arduino 101 can do, some background of the peripherals and the sensors that ship built into the board, and in particular to the Intel microcontroller, the Curie microcontroller. Hopefully have a good understanding of what you can do with the integrated Bluetooth low energy, with the motion sensors, and in general with what you can do with this board.